Okay, so if these are the systems defining x, a, and f, and if we have the usual system in normal form, then this system of equations, second order, third order, two equations, 3, 4, up to n, becomes dx dt, where we're taking the derivative of this matrix, defined initially, equal to, what would you say? How do I get all of this from what we have up here? Yep. Very good. Okay. So it is going to be a little nicer to think of what we're looking at as just one equation. Now, if the system is homogeneous, all that means is that all the f functions, f1, f2, and so on up through f sub n, are equal to 0, so we don't have this f of t. So if it's homogeneous, then it simply becomes dx dt equals a of t times x. Okay, so let's look at an example here, just getting used to the notation. Let's say we have dx dt equals minus 2x plus 5y plus e to the t minus 2t, and dy dt equals 4x minus 3y plus 10t. So we're going to write this system with the new notation. So now we're trying to solve for x and y. So if we let our solution vector x equal x and y instead of x1 and x2 and so on, then this simply becomes what? Good. And now here's our n by n matrix. Coefficients are -2, 5, 4, -3. That's our A. And then we have x. And now if this were homogeneous, if we didn't have these extra functions attached at the end, then this would be our answer. Okay? And we'll deal with a lot of those later because those are pretty easy to solve. But since we do have two separate functions, what I would do is this. Looks like you have an e to the t, and you also, as a parent function, and then you also have t as a parent function. So then you simply just figure out, all right, in the first equation, I have how many e to the t's? That's just 1. In the second one, there are 0 of them. and then the following one would be -2 and 10. Okay. Any questions on that? Okay. Moving on. The definition of a solution vector is a solution vector on an interval I is any column matrix X defined as, well, whatever we need it to be, but x1 of t down through n of these, x1, x2, x3, and so on, or x, y, z, whose entries are differentiable functions satisfying, let's see, what did I call it? Let's call this equation 1. So if they satisfy that equation in orange, then that's what we consider the solution to the system. Okay. Pretty basic. Let's try this. Verify that x1 equals 1, -1 times e to the minus 2t, and x sub 2, which will equal 3, 5 e to the 6t, are solutions of x prime equal to 1, 3, 5, 3 times vector x Okay. So all we have to do is basically plug in x1 into the equation. I would start by taking the matrix 1, 3, 5, 3 and then multiplying it with x1. If I take x1 and write the entire thing as a matrix, this would become e to the minus 2t, and then negative e to the negative 2t. Hello. Okay, thank you. Okay, so if you actually multiply this out, this is a 2 by 2 times a 2 by 1. You're going to get a 2 by 1 matrix. Anybody have it yet? One times e to the minus 2t. Add that with 3 times negative e to the negative 2t. That gives us negative 2 e to the negative 2t. And now we take the bottom row, dot it with the only column that we have. We have 5 minus 3, so that's 2 e to the negative 2t. So there's the right-hand side of the original system. If I go ahead and compute the left-hand side, which is just the derivative of x1 prime. So if I go back to x1, we're taking the derivative of e to the minus 2t and negative e to the minus 2t, which is exactly what we have above. So x1 is a solution. And if we go ahead and repeat for x2, the 1353 times x2 is 1353 times, what was it? 3e to the 6t, 5e to the 6t. Multiply those out, we have 3 plus 15, which is going to be 18 e to the 6t. Then we have 15 plus 15, that's going to be 30 e to the 6t. So again, that's our AX. And if I look at x1 prime, take the derivative of 3e to the 6t and 5e to the 6t, and we get, of course, 18e to the 6t. Whoops, not a fraction, sorry. And 30e to the 6t. So x2 is a solution. Okay, keep this example in the back of your minds. I'll refer to it later. Any questions on how to verify solutions? Because I don't think there should be, but you never know. Okay. Now, what you're about to see may be a bit repetitious, because the theory for systems of differential equations is pretty much the same theory we've talked about before. You'll see a lot of the same names. So repetitious, yes, but nice because you're going to be familiar with it. So let's go through an IVP. So we're going to let T naught be in some interval I for our solution, or interval of validity for the solution. And x of T naught is going to produce a column matrix, which is simply the entries when you plug in T naught into x1, x2, all the way through x sub n. and we'll let x naught, bless you, equal gamma 1, gamma 2, and so on. Okay, so the problem is going to look like this. Solve dx dt equal to a of t times x plus f of t subject to some kind of condition which is going to look exactly like this x of t naught equal to some initial column matrix, which is this guy over here. So it looks a little different, but it's the same idea. You're given an initial value, but they're going to satisfy all of the equations. Bless you. Let's see. What other things did we talk about? How about existence of a unique solution? Let a of t and f of t have entries that are continuous functions on some common interval I that contains the point t naught. Pretty easy. As long as this is met, then there exists a unique solution to the IVP. So as long as you have continuous functions on the same interval, and that interval contains that initial value, then there will be a unique solution to the IVP. Okay, and we're going to assume that this is the case, just like we did earlier when we were solving nth order equations. And that's pretty much all we need to know there. Let's see. We also talked about something called the superposition principle. It's going to look pretty much the same. Let x1, except now it's column matrices or vectors, x1, x2, x sub k, be a set of solution vectors of the system x prime equal to ax. Then x equals what is also a solution? Say that louder, sorry. That, in addition to any general constant, c1, x1 plus c2, x2 plus c sub k, x sub k, is also a solution. Okay. So referring back to the first example, was it the first example we did? The second example. Whatever the previous one was. We verified that x1 which was 1, negative 1, e to the negative 2t, and x2, which was 3, 5, e to the 6t. These were solutions, right? To the system x prime equal to 1, 3, 5, 3, x. Then by superposition, we know that x equals c1x1 plus c2x2 is also a solution, and if I write that out, that's just c1 times e to the negative 2t negative e to the negative 2t plus c2, 3 e to the 6t and 5 e to the 6t. And this is also a solution. Okay? No one's lost, I hope, including those who are half listening. Okay. Linear independence. You could probably guess what I'm going to talk about if you remembered what we did a few units ago. It's the same exact thing. Let x1, x2, x sub k be solution vectors of x prime equal to ax. We say the set is linearly dependent. If there exists constants C1, C2, C sub k such that you can linearly combine them so that when you add them up, you get what? Not just 0, but the 0 matrix. If not, then the set is linearly independent. So the same kind of principles from before are going to be the same. If you have two solution vectors and they're multiples of each other, then obviously they're going to be linearly dependent. Okay? If you have more than two solution vectors, you know what, I should probably go back and say C1, C2, C sub k, not all 0. If you have more than two solution vectors, As long as one of the solution vectors can be combined using the rest of them, same idea. We get linearly dependent. Okay. Wronskian. Let x sub 1 be x1, 1, x1, 2, or sorry, that should be 2, 1. Down to x sub n1, x2 equals x1, 2, x2, 2, x sub 2n, or no, nth row, second column. It's kind of strange when I separate them like this. And so on. X sub n, first row, nth column, second row, nth column, all the way down to x sub nn let all of those be solution vectors to x prime equal to ax if the Wronskian of these solution vectors which is simply equal to the determinant of the n by n matrix as you put all of these together. So this whole thing here is x1, this whole thing here is x2. You get the idea. If the determinant does not equal 0, for every value in the interval, then the set of solution vectors is linearly independent. We'll finish with an example and call it a day. Show that x1, so we're sticking with that same scenario from before, just making sure I have the same 1, negative 1, e to the negative 2t, and x2 equals 3, 5, e to the 6t. Show that these are linearly independent. All you have to do is compute what? compute the Wronskian of the two solution vectors, which is the 2 by 2 determinant of e to the negative 2t, negative e to the negative 2t, and 3e to the 6t, 5e to the 6t. If you compute the determinant, you get 5e to the 4t plus 3e to the 4t, which equals 8e to the 4t, which never equals 0 for all t. Therefore, x1 and x2 are linearly independent. Okay. Good place to stop. We will finish this section. There's not much left, but probably another half hour. Today is Wednesday. Tomorrow is bad, right? As far as people being here. Who will be here? Oh, wait a minute. 9. It's about half the class. Anyone gone on Friday? Okay. Maybe what I'll do is go ahead and finish this tomorrow, post the video. Friday will leave as a packet day, so those that are gone,